Hey, and welcome to the lesson on the rational root theorem, which is also known as the rational zeros theorem. Either way, welcome to the lesson. In a previous lesson, we kind of got stuck trying to solve a polynomial because we didn't know where to start. We didn't know anything about possible roots, and there was no way to factor it. So, that's where the rational root theorem comes in. So our objective is to apply that rational root theorem to actually be able to solve a polynomial that before we couldn't. So our essential question, what if we aren't just given some of the roots of a polynomial? And again, your common core standards are below. So this is the rational root theorem. This is what the textbook has it look like. Pretty much saying for any polynomial function, you're going to look at the leading coefficient and the constant term, a and z. You're going to take factors of z, all the factors of z, and list them out. You take all the factors of a and list them out. And you're going to put them in the form of plus or minus p over q, where p is a factor of z, and q is a factor of a. So for example, below you see factors of 3, which is the constant term. So p equals 1 or 3. And then q's, factors of the leading coefficient 6, 1, 2, 3, or 6. And then under that, you see p over q, all the possibilities of p divided by q. So the factors of z divided by the factors of q. It's a really great two-part lesson by a guy named Derek Owens. He calls it the rational zeros theorem. Same thing. But really take a look at this video, take some notes, really think about what he's doing and what he's saying. I know it may be tricky and confusing, but hang in there and I'll be back to explain it some more and go through a practice problem with you.
Okay, now we're going to talk about the rational zeros theorem. And what I'm going to do is explain to you what the theorem says, and I'll do that by working through a simple example. And then I'll come back and explain to you why the theorem works. And then we will work through a few more examples and I'll point out some important concepts and ideas along the way as we work through those. Let me say before we get started that you need to understand synthetic division before you try to tackle this. We will use synthetic division a lot as we work through examples that involve the rational zeros theorem. So make sure you have that down. If you need to, go back and get that squared away before coming back to this. But here we go, the rational zeros theorem. The rational zeros theorem says that if you need to factor a polynomial, such as this, 2x cubed minus 5x squared minus x plus 6. If you need to factor this, you can look at this number here, what we sometimes call the constant term because there's no variable there, and this number here, which we sometimes call the lead coefficient because it's the coefficient on the lead term. You look at those two numbers and you take this one and that one, and in this case we will think about factors of 6 over factors of 2. So let's think about the factors of 6 real quick. That's easy. 1, 2, 3, and 6. Those are the factors of 6. And we could have positive or negative. And divide those by factors of 2. 1 or 2. So let's make a list of all the possible fractions we could make by using one of these numbers over one of these numbers. So we'll do this systematically. We'll start here with 1 over 1, which is just 1. And then next one we'll do 1 over 2, which is a half. And then for the next one we'll do 2 over 1, which is 2. And then we'll do 2 over 2, which is 1. That's already in the list, so I'm not going to rewrite it. But then I have 3 over 1, which is 3, so that's my next one. And then 3 over 2, which is 3 halves, so I'll put that in the list. And then I have 6 over 1, that's 6. And then I have 6 over 2, which is 3, and that's already in the list. So this list is all of the possible numbers that can be made by taking a factor of 6 and dividing it by a factor of 2. And I'll put a little plus minus out front. And that plus minus applies to all of these. And what I've done here is not really a standard notation, but I think my meaning is clear. I mean all the possible numbers that can be made by doing this, taking factors of the constant term divided by factors of the lead coefficient. The rational zeros theorem says that this is a good place to look for zeros of this polynomial. In fact, if there are any zeros of that polynomial that are rational numbers, and you see the name there, rational zeros, if there are any zeros of that polynomial that are rational numbers, then they will be in that list. So what we'll do now is just try them, and I'm going to start at the beginning and work through them one at a time and see if we find any that are zeros. So we'll start with 1 here. Okay, so I set up the synthetic division and I write down my coefficients 2, -5, -1, 6, and let's see if this works. We're going to be seeing if x minus 1 is a factor. So bring down our 2. 2 times 1 is 2. We add, we get -3. Times 1 is -3. We add, and we get -4. -4 times 1 is -4, and we add and we get 2. So that one didn't work. So let's try the next one, 1/2. So we'll set up the synthetic division here, 2, -5, -1, 6. And we bring down the 2. 2 times 1/2 is 1. And we add right here, and we get -4. -4 times 1/2 is -2. And we add there, and we get -3. -3 times 1/2 is -3 halves. And we add there, and we get 4.5. Or 4.5. That one didn't work either. So let me free up a little bit of space here. So let's try the next one, the 2. And I write down my coefficients, 2, -5, -1, 6. And bring down the 2. 2 times 2 is 4. We add and we get -1. -1 times 2 is -2. And we add there and we get -3. -3 times 2 is -6. And we add and we get a 0. Aha. Right there. We have found a factor. The fact that we get a 0 remainder down here means that x minus 2 is a factor, and these other coefficients give us the other factor. So this polynomial up here, our original polynomial, factors as x minus 2, and then we look down here, x squared minus x minus 3. Oh, excuse me, that's a 2 right there. 2x squared minus x minus 3. So we've factored our polynomial. Now, we could go on and factor this. That's a quadratic. We can always factor a quadratic. The point here, though, is that we have found a factor. Using this list of numbers and synthetic division, we found a factor of the polynomial. And we found that factor by using the rational zeros theorem, which says that if there are any factors or any zeros of this polynomial that are rational numbers, that they will be in this list, and that list is found by taking factors of the constant term, dividing by factors of the lead coefficient.
So welcome back. That was the first part. So I hope you really understood it. You took some notes and you paid attention. Here is the second part. Now, if you didn't fully understand the first part, make sure you go back, because you won't be able to understand the second part if the first part is still a little unclear. Here is the second part of the video.
Now let's look at why the rational zeros theorem works. Think about this example. X plus 2 times x minus 5 times x plus 3. Okay, let's multiply this out and watch the numbers. Watch what happens to this 2 and this minus 5 and that 3 as we do this. To multiply this out, I'm first going to do a FOIL right there, and I'll leave this term over here. So doing a FOIL over there gives me a x squared, and then I have minus 5x and a plus 2x. So that gives me a minus 3x. And then 2 times negative 5 gives me a minus 10. And then I still have x plus 3. So now I need to do x times each of these terms, and then 3 times each of these terms. So I'll do it in that order. I get x times this is x cubed, then minus 3x squared minus 10x, and then a plus 3x squared, and then a minus 9x, and a minus 30. And these cancel out, the minus 3x squared and plus 3x squared. That's kind of nice. Doesn't always happen that way, but it did here, which is fine. And we get a x cubed minus 19x minus 30. Now we ended up with a 30 as the constant term. Now, where did that 30 come from? Well, that 30 right here came from up here. So that 30 is there. And where did that 30 come from? Well, it came from this 10 and this 3. So those two numbers multiplied together gave me that 30. And where'd the 3 come from? Well, the 3 came from right up here. And this minus 10 came from that 2 and that minus 5 multiplied together. So you can see, you can trace it through there with those arrows that I've drawn. That 30 came from this 2 and this 5 and this 3. And even has this minus sign carried all the way through right there. That constant term right there at the end came from my original factors. And so you can see that the zeros of this polynomial, and the zeros are easy to see right there. You can see that x is negative 2, x is 5, and x is negative 3. Those numbers are factors of 30. So it should make sense that if you're trying to find factors of this polynomial, a good place to start would be factors of 30, because this term is always going to come from the numbers up there in those original factors. So again, if you're trying to factor something like this, then the factors of that number are going to be a good place to start looking. Okay, so here's an example. Suppose we're told to factor x cubed minus 4x squared minus 4x plus 16. Well, factors of 16 are going to be a good place to start looking for zeros. So factors of 16, those are going to possibly be zeros of this polynomial. So what are the factors of 16? Well, they could be positive or negative. 1, 2, 4, 8, and 16. So let's try those. We'll start off, we'll try 1. So let's set up the synthetic division. 1 here, and we get, well, let's write our coefficients here. 1, minus 4, and 16. And let's do the synthetic division. Start with 1. 1 times 1 is 1. 1 plus negative 4 is negative 3. Then we multiply by 1 again, and we get negative 3. And we add here, and we get negative 7. Negative 7 times 1 is negative 7, and we add, and we get 9. So that didn't work. So let's try the next one. And we could go all the way to the end and not find anything, and then come back and have to try the negative numbers as well. But we'll just be systematic here. Try 2. Okay, so we set up the synthetic division here. And we start with the 1 over there on the end. At the beginning here, bring the 1 down. 1 times 2 is 2. We add negative 4, and 2 is negative 2. Then we multiply. Negative 2 times 2 is negative 4. And we add here, and we get negative 8. Negative 8 times 2 is negative 16. And we add, and we get 0. And we found it. A 0 remainder means that x minus this number is a factor. And in the other factor, we'll have coefficients that we get from those numbers down there on the bottom. So the polynomial factors as x minus 2 times x squared minus 2x minus 8. And then we can try to factor this quadratic. So let me scroll down here, get a little more room. And that quadratic actually isn't too hard to factor. We're going to need x plus something and x minus something, because this 8 here is negative. And so what works there? It looks like x plus 2, x minus 4 will work, because that certainly gives us an x squared. And then the outer and inner gives us a minus 4x plus 2x, so that works. And then the 2 times negative 4 gives us negative 8. So we've got it. We factored this, and we found our original factor using the rational zeros theorem.
Okay, so I hope you learned a lot in those videos. I know they were long, but I really thought that they were worth it. So let's put it to use now. And if you have to take, some time off from watching this video and then come back to really work on this, if sitting down for this long is too much, don't be afraid to pause this video and come back when you're ready to work through this problem. So I don't know where to start on this problem. So I'm going to use the rational root theorem. So I need to take factors of 12 and factors of 2. So factors of 12 divided by factors of 2. That is going to give me all my possible zeros. Okay, so let's start with 12. I have 1, 2, 3, 4, 6, and 12. Plus or minus. Don't forget, plus or minus, plus or minus. Those are all my factors of 12. And my factors of 2 are 1. So all of these divided by 1, so they would just be themselves. And then any one of those divided by 2 as well. So I could have 1 or negative 1 divided by 2. So I'm going to include that in my list. So I can add plus or minus 1/2. Then I can have plus or minus 2 over 2. Well, that's just going to give me plus or minus 1. So I already have that in my list. So I don't have to include that. Plus or minus 3 over 2. I don't have that yet, so I'm going to include that over here in my list. Plus or minus 4 over 2. Well, that's just going to give me 2, so I don't need that. Plus or minus 6 over 2. Well, that's just going to give me 3. So I already have that. And plus or minus 12 over 2. Well, that's going to give me 6. So, and I already have that in my list. So here's my list of all the possible zeros. So I'm going to use the remainder theorem to see if they work. So I'm going to start with testing number 1. So if I try 1, I'm going to substitute 1 in for all the x's. I'm going to get 2 minus 3 minus 8 plus 12. Now if it's a 0, if the answer is 0, that means that 1 is a 0. 2 minus 3 is negative 1, minus 8 is negative 9, plus 12 is 3, so does not work. Not a 0. Then I'm going to test negative 1. So this seems like a lot of work, but it's one of the only ways to factor. It is the only way to find a possible 0. So we have to do our due diligence and do it. It's not so much difficult as it is tedious. I know it is time consuming. So I'm going to use negative 1 now. So I'm going to have negative 1 cubed is negative 1, so negative 2. Negative 1 squared is positive 1, so minus 3. Negative 1 times negative 8 is a positive 8, so plus 8, and plus 12 equals negative 2 minus 3 is negative 5, plus 8 is positive 3, and plus 12 is 15. It does not equal 0, so it is not a 0. Now I'm going to test the number 2. Okay. 2 cubed is 8, so 2 times 8 is 16. Negative 3 times 2 squared, which would be 4, so 3 times 4 is 12, so 16 minus 12. Minus 8 times 2, which is 16, so minus 16. And plus 12. What does that equal? Well, 16 minus 16 is 0. Negative 12 plus 12 is 0, so look at that, 0. Yes, this is a root. So that's awesome. We found it. Now, you could keep going through all these numbers to find all the zeros. Or, since you have 1, what we can do is we can use synthetic division to factor it out, right? So 2, I'm going to do 2, negative 3, negative 8, and 12. If I do my synthetic division, we bring this 2 down. 2 times 2 is 4. Negative 3 plus 4 is 1. 2 times 1 is 2. Negative 8 plus 2 is negative 6. And negative 6 times 2 is negative 12. And it indeed does give us a remainder of 0. So my resulting, so don't forget I did x minus 2. Don't forget this is minus. If x equals 2, that means x minus 2 is our factor, and that's what equals 0. So that's my factor is x minus 2. My root is 2. And so my resulting quadratic is x squared plus x minus 6. And from there I can say what multiplies to 6 and negative 6 and adds to a positive 3. And I'm going to say x minus 3 and x plus 2. From there, I get 0. And I get x equals 3 and x equals negative 2. And there you have it. Those are all 3 of our roots. Why 3? Again, because the polynomial is of degree 3, therefore there are 3 solutions. And those 3 solutions are negative 2, positive 2, and 3. So thanks so much for sticking through with this lesson. I know it was a lot, but I really hope you learned something. Hope you can use it well on your homework. If not, if you still have some questions, make sure you go back through the video, give it a second glance, take a look through your notes. And then you can always reach out to me on BBIM or text message or phone call, whatever's easier for you. And I hope to see you in live class where we can go through this a little more in depth.